developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, my name is Guanyin Wang.
My name is Shubhra.
We're a graduate student at UW Medicine, and we're working on the deposition of high-quality nucleation layers.
This film will be used for epitaxy of thick gallium oxide fiber layers on thermally conductive substrates.
Through this project, we are trying to tackle the root cause of reliability and lifetime issues faced by gallium oxide-based devices. If successful, our technology will have a far-reaching impact on AFRL's mission of pushing the performance limits of gallium oxide by providing a pathway for through-substrate heat extraction.
Here at the Air Force Research Laboratory, Materials and Manufacturing Directorate, we are interested in gallium oxide for high-power electronic devices and next-generation platforms. Its large bandgap allows it to handle larger voltages, which are required for these platforms. Additionally, access to bulk substrates make it easy to manufacture high-quality semiconductor devices. However, gallium oxide lacks the ability to properly remove heat from the high voltages and currents it experiences during operation due to its low thermal conductivity. The collaboration with the University of Wisconsin, enabled by the Midwest AFRL Regional Network, enables an innovative solution to this challenge. By using materials such as silicon carbide and diamond that have higher thermal conductivities, and nucleating gallium oxide layers on them, the limitations imposed on gallium oxide due to its relatively poor thermal conductivity can be relieved. Without this program, an innovative solution like this would not have been properly investigated. By realizing the successful deposition of high-quality conductive gallium oxide films on these solid-phase epitaxy substrates, the potential of gallium oxide electronics can be pushed past its current limitations and enable new functionality in Air Force platforms.
Our method involves the deposition of amorphous gallium oxide followed by annealing of the layer at high temperature. Then we'll work with our collaborators to get thick gallium oxide buffer layers deposited on these thin crystallized gallium oxide layers. We will utilize 4 key equipment. The first will be the RF sputtering tool that allows us to deposit amorphous gallium oxide films. Next, we crystallize our films at 900 degrees Celsius for a few hours in a muffle furnace. It is crucial for us to evaluate the quality of the material that we deposit. For that, we use 2 characterization tools. The first is an X-ray diffraction tool, and the second is an atomic force microscopy tool. Since the start of this project, we have been able to achieve high-quality single crystalline gallium oxide films on both sapphire and silicon carbide substrates. We have been able to achieve an order of magnitude lower surface roughness compared to gallium oxide films deposited on these substrates using other deposition techniques, which is highly encouraging thanks to this funding. The atomic force microscopy image on the right shows extremely smooth films, and the X-ray diffraction plot on the left shows single crystalline behavior of the deposited and crystallized gallium oxide films with solid phase epitaxy technique. Over the last 6 months of research, we have made tremendous progress. We have been able to demonstrate heteroepitaxy of crystalline gallium oxide films on various substrates with record surface roughness and material quality. Our first 6 months deliverable was to demonstrate phase-pure crystalline gallium oxide films on a thermally conductive substrate with a surface roughness of less than 1 nanometer across a 5 micron cross 5 micron atomic force microscopy scan. The results I just shared were on sapphire substrate, which is readily available in large sizes and is quite economical, but its thermal conductivity is only slightly better than that of gallium oxide. Very recently, we have obtained phase-pure gallium oxide films on silicon carbide substrates. We chose silicon carbide because its thermal conductivity is 10 to 30 times higher than that of gallium oxide. A prior report of epitaxial gallium oxide film on silicon carbide substrate has shown high thermal boundary conductance between the gallium oxide and silicon carbide substrate that promises effective heat removal through the substrate from the gallium oxide films. While this demonstration was encouraging, the surface roughness obtained for these films was high, that is close to 2.5 nanometers. We have met our deliverable of achieving phase-pure gallium oxide films on silicon carbide substrates with a surface roughness of less than 1 nanometer, which is 3 times lower than the best reported surface roughness for gallium oxide on silicon carbide that I just shared. The phase purity has been confirmed with X-ray diffraction and is part of our ongoing optimizations that involve pre-annealing of our substrates prior to gallium oxide film sputtering at a high temperature. With these encouraging results, we hope that the AFRL Midwest Hub supports our efforts going forward. Thank you for your attention.